Hello, let me talk about plastic analysis of structures. So let me begin. Now we know that there are two approaches in engineering design in general, that is working stress approach and limit state approach. Now in working stress method, or which is also called as WSM, the allowable or safe or working or permissible or service stress is given as yield stress sigma y by factor of safety. So here at the left side I have shown on graph of a ductile material like a mild steel bar which is subjected to tension. So it is stress versus strain curve. Now here we can see that sigma y is the yield stress corresponding to yield point. Sigma u is the ultimate stress corresponding to the maximum load which that material can carry, and sigma a double L, that is sigma allowable or sigma safe, or you can say sigma permissible stress. So that sigma allowable is got by dividing yield stress sigma y by a suitable factor of safety. Uh, that means in working stress method, the stress is restricted to sigma allowable under the service loads or the permissible loads. Here, the load factor is not applied, means the loads are not multiplied with any factor, and therefore the structure is subjected to only elastic analysis. Now going further, now next method or next approach is limit state method. Uh, we know that the structure is designed for limit state of collapse or limit state of strength. Then we apply the serviceability checks to check the serviceability of structural elements like deflection or maybe cracking or maybe from durability point of view. Now here in limit state method, partial safety factors are applied on loads as well as stresses. But let us see this limit, why limit state design is still a conventional approach. We know that limit state method is better than working stress method, but still it is conventional approach only. Why? Because linear analysis, linear elastic analysis carried out here. However, for limit state values of bending moment, shear force and axial force, the load factors are multiplied. That means bending moment, shear force and axial force, they are multiplied with certain load factors. Non-linear analysis used only for the design of the section. This is really contradictory because we are using elastic analysis for initial stage, and only for design we are using non-linear analysis. So this doesn't go hand in hand. Now what are the limitations of conventional analysis approach? Now here I have shown on simply supported beam AB of length L, where a symmetrical load is applied at the center, load P, and here this diagram shows the bending moment diagram. Obviously the maximum bending moment will occur at the center, which is PL by 4, that is load into span by 4. So if the section is symmetrical, there are only 2 points which reach the yield stress. So here second diagram clearly shows that the yielding has started only at the 2 points, that too at the center, because that is the point where maximum stress will reach first because of the symmetry of loading. And here the third diagram shows that above the neutral axis there is compression and below the neutral axis there is tension, because it is simply supported beam, and the stress, yield stress sigma y, is reached at the 2 points only simultaneously. However, if the structure is not symmetrical, then only one point will reach the yield stress. Now the moment corresponding to this yield point is called as yield moment My. However, structure has not reached collapse stage or collapse state at this stage. This is very important. That means the structure has not yet reached the collapse state at this stage. That means only yielding has started, whereas the structural element is still capable of carrying further loads. And therefore, let us see the significance of plastic analysis. In conventional approach, that means in limit state method, it is assumed that structure has already failed at yield moment only. However, it is not practically true. The structure is capable of taking more loads as well as more bending moments even beyond the yield moment, because here the P ultimate is much greater than Py. That means the ultimate load is much greater than yield load. Similarly, M ultimate is much greater than My. That is ultimate bending moment or ultimate moment, you can say simply, is much greater than yield moment. More significantly, My and Py, that is yield moment and yield load, they are correspond only to the yielding at only 2 points. That means when we take My and Py, they correspond to only yielding at 2 points, means where maximum stresses are reached. All other points they remain under stressed, and that again becomes uneconomical. Whereas we have to actually take the load factor as P ultimate by Py. That will be more realistic. In conventional approach, the limit state design method is restricted only for the design, not for the analysis. Whereas plastic analysis extends this for the load analysis as well. So that means actual structural behavior even beyond the yield point is considered in plastic analysis, and that is the major significance of plastic analysis. In other words, actual structural behavior at collapse is considered. Now, what are the various assumptions in plastic analysis? Hooke's law of elasticity, as we studied in mechanics of structures, it is valid till yield point. That is, stress strain curve is linear till the yield point. Young's modulus as well as yield stress sigma y have same values for compression as well as tension. Stress strain curve is similar in compression and tension, whereas strain hardening is not considered. We know that for a ductile material like mild steel, beyond the yield point, the material again undergoes the strain hardening, and that's why load carrying capacity goes on increasing even beyond yield point. But here in plastic analysis, the strain hardening is not considered. So here left, it is actual stress strain curve obtained from the laboratory, whereas right side is idealized. That means this side I have shown left side compression and right side I have shown tension. That means the curve is assumed as a flat after the material has reached the yield stress. You can clearly see in tension as well as compression. Now one more assumption, that section has at least one line of symmetry. That means the plastic analysis is applicable only to those structural elements where at least there will be one line of symmetry. For example, here you can see T section. It is monosymmetric because it is symmetric about only one axis, that is vertical y axis. Whereas here I section, that is, it is bisymmetric. It is symmetric about x axis as well as y axis. This is because if the plane of loading and plane of bending, if they do not coincide with each other, or they do not coincide with plane of symmetry rather, then the formulations of plastic analysis will not apply. For example, if I see the last figure here, here you can see that the plane of loading and plane of bending, they are not coinciding with plane of symmetry, and therefore I have clearly written here that plastic analysis is not valid for such kind of structural elements. Now, regarding materials, we can see where is the applicability of plastic analysis. For high tensile steel, plastic analysis is not applicable. The reason is high tensile steel doesn't possess a well-defined yield point, and there is absence of horizontal part in stress strain curve. Aluminum alloys, it is applicable. However, it is applicable with certain modifications. Brass, it is not applicable at all because brass is a brittle material. RCC, that is reinforced cement concrete, is applicable. However, it is not applicable in a similar manner as it is applicable to ductile material like a steel, because there are certain limitations on rotations. Whereas mild steel, it is straightway applicable because it is ductile material, so it is applicable. So this is what I wanted to tell. Thank you very much.